Hello, everyone. Happy holidays wherever you are in the world. It's been a while, but I am back with another scripting tutorial for you guys. This time, talking about how to create a dash system. In the previous tutorials, we went over how to create a sliding system. So if you haven't checked that out, I definitely would. But yeah, let's get right into it. First, I will show you a quick demo of what the final result will look like once everything is said and done. As you can see, our camera is in regular mode, and in regular mode, you can see we have a forward rolling animation that plays in the direction the character is moving. And when I'm not pressing any keys and I press Q to dash, he will by default just roll backwards. And then in shift lock mode, there's the introduction of two additional animations. One animation specifically for dashing to the left, another animation for dashing to the right. And that's it. Let's get right into the coding portion. Before we get to coding, I should show you what all the assets are that we are using. So for one, we have our animations, our dash animations. And as I said before, we have a backward, forward, left, and right. And we will be using one module called the promise module. And we're going to be invoking on that quite a bit in this tutorial. So I will link the promise module down in the description box below. But otherwise, I think we are good to start. For starters, I've went ahead and inserted some boilerplate code for initializing our services that we will be using. And here I've referenced the promise module. And here are just some commonly used variables we'll need. So one thing we will need to do is to correspond the directions our character moves in to the animations for shift lock. Because if you recall, I mentioned that for shift lock, we play different animations based on direction, whereas in regular camera mode, we just play the forward animation. So I'm going to create a table called directions, which will be a mapping between these animation name prefixes and directions. And then now we're going to go ahead and load our animations so that they are available when we want to play them. So I'm going to loop through the dash anims folder. And if a particular instance or descendant instance in the folder is an animation, then we want to load that animation. And there we have it. So the way the movement is going to work is we want to quickly accelerate the character in the direction and then quickly decelerate his speed to 0. So to do this, we're going to use some basic projectile motion equations and concepts to help us. And we will need a basic function to help us with this. We'll call this function accelerate to velocity. And this will take a linear velocity instance. It's going to take a target velocity. This will be the velocity that we're trying to reach, target velocity that we're trying to reach, and then xl will be the how fast we want to reach that target velocity, so the acceleration to that target velocity. We're going to create a velocity variable. This will be our current plane velocity. And if you're not familiar with linear velocity, plane velocity is basically a property that allows us to apply velocity only within a certain plane. And in our case, our plane will be parameterized by the x and z axes, because we don't want, for example, if there's some sort of gravity also affecting the character, which would happen in the vertical direction, we don't want to affect any movement or touch any movement along the vertical direction. We only want to move the character along the lateral plane. And so this should actually be a vector 2, because like I said, it's the x and z axes, and therefore this should also be a vector 2 as well. And we're going to create a variable delta v. This will be the difference between our target velocity and that plane, our current plane velocity. I'm going to type this line out first and then explain after. If you're not familiar with delta time, pretty much it's the amount of time that has elapsed between the previous frame and the current frame. So essentially, it's a factor of our FPS. So if you're having 60 FPS, then on average, each frame is taking 1/60 seconds. And you'll understand why we need this with this next line. So max acceleration here is the maximum acceleration that can be possibly done within a frame, right? So when we're dealing with game development, frame, the time it takes to complete one frame is our most basic unit of time. So if you're expecting something to accelerate within a span of time that is shorter than a single frame, then we cannot reasonably do that. So this is the best we can do. So this is a cap, essentially. Now let's create a variable called final acceleration. So we're going to see if the acceleration that we're trying to accelerate with is if our maximum acceleration is less than what our input acceleration, then we're going to just set the final acceleration to the maximum acceleration, because essentially we're trying to accelerate faster than what is possible. Otherwise, if we're not, then we're just going to take MacXL. We're going to just take unit vector and then multiply by acceleration. So we're saying that we want within the same direction as the delta v, but we make a unit vector so that the magnitude of our acceleration vector will be equal to our input acceleration. And just remind you, this is just a regular number. And then finally, we're going to return a promise. More on this later. And I'm going to create this frames within reach variable, which I'll explain in a bit. I'm going to say game : get service, run service, stepped. So that's stepped because we want to change our velocity prior to the physics step. So before any sort of physics simulation is done within the frame. So if you're familiar with heartbeat happens after physics simulation. But since we're trying to modify the velocity, we want to modify the velocity prior to the physics simulation. And so we're going to modify our current velocity. And remember, we're trying to modify our current velocity such that it is, we want to accelerate it. So we're going to take our current velocity and we're going to add it to final acceleration times dt. So let's say that our final acceleration was like 3 meters per second squared. So when we multiply by dt, we're multiplying it by the time it takes for a frame to elapse. So over the course of 1 second, we would have added 3 meters per second to our velocity. And now we have to test if we have reached our target velocity. So we're going to take target velocity and then subtract plane velocity. And I'm going to see if that magnitude is less than acceleration dot magnitude times dt times frames within reach. So to explain, basically we're trying to see if our target velocity, if our current velocity is close to our target velocity. And to do this is not so trivial. Some of you might think, why don't we just choose some random arbitrarily small number like 0.0003, and if it's less than that, then we have reached. But we want to be more exact than that. Basically, I'm saying that if we're close to our target velocity by 1 frame, meaning within another frame we'd have reached our target velocity, then then I'll consider that as reached, because we don't want to compare directly against 0, because we're dealing with floating point decimal values and such. So when you're dealing with floating points, you have to always work within a certain range. You can't be exact about it. And also, this is helpful because we don't want to overshoot, right? Because maybe our target velocity, maybe our acceleration is really big. And if our acceleration is really big, then perhaps whatever range that we chose is very possible to overshoot that range. And then this actually becomes like, this becomes like negative sort of thing. And then the magnitude overshot the range where it was close to 0. So this is a very precise way of making sure that we don't overshoot our ranges. All right. And so if we are within reach, then Might as well set plane velocity to target velocity. Disconnect this stepped event. We're going to resolve our promise thread so that any threads that are waiting for this promise to complete will be notified and carry on. So there's two things we will want in our dash system. One of those being, as I've mentioned already, we want the initial burst of speed to be quick, so quick acceleration. And, obviously we want, a good deceleration as well. But we also want to take as input the distance that we want the character to travel over, the period of him dashing. We want this to be predictable. So if I input that, I want the character to dash 16 studs, the character should be able to dash 16 studs. And this predictability is very nice. Well, for one, just in terms of gameplay and playing the game, maybe you have a certain ability and, it causes the character to dash in this manner. And maybe you have a tooltip and you want to show that, hey, this ability will have the character move 16 studs. So that predictability is important in that context. And also in the context of exploit prevention, because here we're doing everything on the client and removing the character on the client. And, when we have a very predictable way of moving the character, then it's very easy on the server to then verify that the character should be where we expect them to be. Otherwise, then it's possible that the client is trying to exploit. And so with all that in mind, let's go ahead and create a new function, accelerate to distance. This will take as input target velocity, acceleration time. That's within how much time we want to reach target velocity, the total distance we want our dash to cover. And so here is where we will create our linear velocity instance. We will set velocity constraint mode to be plane. We only want to apply velocity within the lateral plane. We'll just set the velocity to vector 2.0 for starters. We want our velocity to be specified in terms of world coordinates. And also our axes as well are going to be specified in world coordinates. These are the axes for the plane. So we have the x-axis and then we have the z-axis. Right. Now we will accelerate the character towards the target velocity. Call on our accelerate to velo function. That's in our linear velocity, target velocity, and for acceleration, we will have target velocity magnitude over acceleration time. So the time we want to take to accelerate from 0 to target velocities. essentially. Target velocity dot magnitude would be your speed. And then, remember, Arc Velo returns a promise that resolves. And once that resolves, we want to call back to this function right here, and it resolves when we reach the target velocity. So we will enter this once we've reached the target velocity. And this is where we will decelerate the character to 0. So from target velocity back down to 0. But recall I mentioned that we want to travel a distance of total distance over the course of our dash. So essentially, we first need to figure out how much distance is left, right? Because, we covered some ground going from 0 to target velocity. And so we want to figure out how much distance is left for us to decelerate from target velocity to 0. And whatever that distance is, we have to figure out what amount of deceleration will cause us to decelerate from our target velocity to 0 within and cover a distance, a specific distance while doing that. Okay. So on my screen here, I have a couple of kinematic equations mapped out. So recall first I mentioned we need to figure out the distance that we covered from going to no speed or whatever to reaching our target velocity. And so that distance here is this kinematic equation. So we have 1/2 at squared, and our acceleration is this time here is the time we took to go from current velocity to target velocity. And then this acceleration is nothing but our target velocity over the time it took us to accelerate to there, so which is t1. And so once we eliminate t1 here, we're left with this simple formula. And so the remaining distance is simply our total distance minus the distance covered on the first half, I guess you could say. And then this equation here is how we can figure out the amount our deceleration value from knowing our initial velocity. In this specific case, our initial velocity is our target velocity, and our final velocity would be 0, because we're going from target velocity to 0. And this is over to d2. D sub 2 here is our remaining distance. So this should give us acceleration needed, and final velocity here is 0, so we're just left with this. So let's go ahead and then plug these formulas into our code. So I've gone ahead and put these formulas here. And now it is time to decelerate. So to decelerate, we use the same function. And this time, our target velocity will be 0. And we want to take a2 amount of acceleration, or I guess deceleration, to do that. And once we decelerate to 0, then we're just going to destroy the attachment, which will also destroy our linear velocity. All right, so now let's put it all together and complete our dash. So I'm going to get the forward animation for the forward dash. I'm going to set the moving direction to be, by default, the assembly linear velocity direction, but we only want the lateral direction, of course. So it's going to be, by default, the direction we'd want to move in. Now, there is some exceptions, and that is when we are in mouse lock mode, then we want to do things a little differently. So recall we have this directions table that's a mapping between the animations and the direction we're moving in. And so what I want to do is I want to figure out which of these directions is closest to my assembly linear velocity direction here. And based on that, I will select the animation. So to do that, I'm going to loop through that directions mapping. Just call this direction name. I guess I'm gonna call this closeness. Essentially, I'm multiplying this vector to HRV Hindenburg report C frame to get a relative to get in world coordinates essentially. So this is pretty much the Hindenburg reports, right vectors, left vectors, up vectors, and basically I'm seeing what the angle is between the all the directions of the character and the direction he is moving in, right? So if he's moving in a direction that is very like left, then I imagine the this left vector would be would be close to our movement vector, and so the angle between them would be small essentially. I'm doing 1 minus that because we want this to be if the closer they are together, because this will essentially what the dot product does is if this is the exact same vector as our movement vector, then this will be 1. If it's perpendicular, then it's 0. So if it's the exact same, that means that's the maximum closeness. So that'll be 1. And so 1 minus 1 would be 0. 0 to indicate that they're super close to each other. That's as close as you can get essentially. I'm just gonna keep it this name. I don't like the name, but you guys know what I mean. Okay, so pretty much this whole thing is just to figure out what is the closest direction to our movement vector. And once you figured that out, then we can go ahead and say our animation will be equal to our anim direction, and then we're just going to add dash to the end, right? Because recall, that's how our animations are named. So one of these directions, and then you just add dash to the end. Okay. Otherwise, if we're not moving, and we want to set our move there to be, because we want to roll backwards, if you recall. I'm going to set the animation to be backward dash. We're just going to play the animation. And then we're going to set target velocity to be 60. And we're going to accelerate to distance. We want target velocity times, recall this has to be a vector too, so we're going to say finger.x, finger.z, .unit, and then we want to take 0.04 seconds, so really fast acceleration to the target velocity, and then we want to travel a total of 18 studs. Once you've done that, so this returns a promise. So if you want to, do something after the entire dash sequence, then you do it within here. I don't have anything special per se, so I'll just leave that alone. And yep, so yeah, that's that so far. And one thing I want to do is I want to actually return a promise that will indicate that this has finished. So we will wait until the animation finishes playing, and that's when this dash will be considered completed. I guess it's maybe better to just do this, because you can chain these promises. And then I'm going to add, so we need to add hook the Q key to this do dash, so that whenever we press Q, it will do our dash. Okay, so I'm going to create, I'm going to bind. when we press the Q key, I'm going to create a is-dashing variable for debouncing, and we are not dashing. Then we're going to say we are dashing. We're going to do dash, and then once we're done dashing, I'm going to set as dashing to false, and that should do it. So let's go ahead and test this. Okay, we got an error. Attempt to index nil with play. Context action service. So our animation might be nil. Oh, we put forward, yeah, I spelled it wrong. That should be correct. Go ahead and play. Oh, only worked once. I think this has to do with our promise. Okay. Yeah, I don't think this right here is proper. I'm gonna just put this into a separate promise because I think I do need that resolve. Or if I want to chain that, I have to do this a bit. I'd have to do it a bit differently than what I did just there. But let's just keep things simple. Once the animation is finished, then we resolve. Not quite traveling that 16 studs or 18 studs that we set it to. So let's see what's going on. All right, so I was able to figure out what was going on. Essentially, we forgot to parent the linear velocity instance to our attachment. And also I've went ahead and replaced some linear velocity here with humanoid move direction instead, because it's more accurate for this use case. And also I replaced some linear velocity with humanoid move direction here instead. And that was all. Oh yeah, and then one more thing is, prior I had this. I changed because, you know, we always want to update the current velocity. We want to increment, we want to add acceleration to the current velocity. Well, you know, we're doing, this is happening every frame, and then this only happens at the beginning. So we're using a stale velocity value essentially. So that should instead be LV.plane velocity. When we play this, you can see that it looks good. I go into shift lock mode, left, right, left, forward. Oh, there's a error. See what that's about. All right, so apparently the error disappears when I remove the dot unit from move direction. Move direction, I believe, is already a unit vector, so it's unnecessary anyways. I think I'm gonna move things around slightly because only one of these happens. And this way we check move direction first. If it's 0, then you do this. Otherwise, we can go ahead and do the shift lock logic. You can can see, pretty smooth. I also created a part here that's exactly 18 units long. You can see here to see if we actually travel that distance. Oops, should really anchor that, but anyways, let's see. You can see travel exactly 18 units. Let's say that you want double the acceleration to target velocity. Perhaps you might want to then double the distance that it travels. So you can double both at once. And boom, double the impact, double the distance. It's going 36 units. This is also useful in the context of knockback, because when you're doing knockback on another character, the quick acceleration, deceleration is very important in that context. So this is not just useful for dashing, but in other contexts where you need quick acceleration and deceleration. And I think this doubling effect is also really cool, because let's say that you have a character here and he shoots an arrow and it hits another character, and then somehow he gets this boon that doubles his shot power. And so when you double your shot power, you would expect the other character to fly double the distance. And it's kind of cool because you can vary the the target velocity to be double while maintaining the same amount of time to accelerate to that, which will give the effect of more power, because more power means quicker acceleration while traveling a longer distance, because obviously if he has more power, then the character will get knocked back further. So yeah, I think that is all for this tutorial. Perhaps in the future we might talk about how to do that exploit prevention aspect of it, so that you can verify on the server to make sure he's traveling the right number of studs. He's ending up and that he's ending up in the correct location. But otherwise, yeah, that is all for now. I'll see you all in the next tutorial. Don't forget to like, subscribe, because this gives me motivation. And if you have any questions, any comments, feel free to drop it in the comment box. And I should mention that this the rolling, the sliding, all this movement comes from a game that I'm currently working on as part of a team called Atlas. So if you're interested in supporting that game, I'll also leave that Discord invite in the description box. Thank you, and happy holidays.